calculate voltage drop, the National Electrical Code provides a formula. This formula is VD equals 1.732 times L times R times I divided by 1000, where VD is the voltage drop in volts, L is the length of the conductor in feet, R is the resistance of the conductor in ohms per 1000 feet, and I is the current in amps. In this scenario, we have a 13.8 kilovolt system with a #2 American wire gauge cable in rigid metal conduit, RMC, with a one-way distance of 1200 feet and a load of 100 amps. The resistance R is 0.2 ohms per 1000 feet. We'll use these values in the formula to find the voltage drop. First, let's identify the known values. The length L is 1200 feet. The resistance R is 0.2 ohms per 1000 feet. The current I is 100 amps. Now let's substitute these values into the voltage drop formula. VD equals 1.732 times 1200 times 0.2 times 100 divided by 1000. Performing the multiplication, 1.732 times 1200 equals 2078.4. Then 2078.4 times 0.2 equals 415.68. Next, 415.68 times 100 equals 41,568. Finally, we divide 41,568 by 1000, which equals 41.568. Therefore, the voltage drop VD is 41.568 volts. Now let's calculate the percentage voltage drop. The formula for percentage voltage drop is percentage VD equals VD divided by V times 100%, where V is the voltage at the source. In this case, V is 13,800 volts. Substituting the values into the formula, percentage VD equals 41.568 divided by 13,800 times 100%. Performing the division, 41.568 divided by 13,800 equals 0.301,217. Then 0.301,217 times 100% equals 0.301,217%. Rounding to 3 decimal places, the percentage voltage drop is 0.301%. In summary, for a #2 American wire gauge 13.8 kilovolt cable in rigid metal conduit with a one-way distance of 1200 feet and a load of 100 amps, the voltage drop is 41.568 volts, which is 0.301% of the source voltage. The National Electrical Code provides guidance on acceptable voltage drop limits. It's important to consult the NEC to ensure that the calculated voltage drop meets the code requirements for the specific application. The NEC recommends a maximum voltage drop of 3% for feeders and 5% for branch circuits. In this calculation, the voltage drop is well within the acceptable limits. Remember that the resistance value used in the calculation is based on the assumption that the cable is operating at its rated temperature. The actual resistance of the cable may vary depending on the ambient temperature and the load current. It's also important to consider the dating factors for conductors in raceways when calculating voltage drop. The NEC provides tables that specify the dating factors for different numbers of conductors in a raceway. These dating factors should be applied to the conductor ampacity before calculating the voltage drop. In addition to the NEC formula, there are also online voltage drop calculators that can be used to simplify the calculation process. These calculators typically require the user to input the same information as the NEC formula, such as the conductor length, current, and resistance. However, they can automatically calculate the voltage drop and percentage voltage drop, saving time and effort. When selecting a conductor size for a particular application, it's important to consider both the ampacity and the voltage drop requirements. The conductor must be large enough to carry the load current without exceeding its ampacity rating, and it must also be large enough to limit the voltage drop to an acceptable level. In some cases, it may be necessary to use a larger conductor than required by the ampacity requirements in order to meet the voltage drop requirements. Voltage drop can have a significant impact on the performance of electrical equipment. Excessive voltage drop can cause motors to run slower, lights to dim, and electronic equipment to malfunction. Therefore, it's important to carefully calculate voltage drop and select conductor sizes that will minimize voltage drop. The 1.732 factor in the voltage drop formula is the square root of 3, which is used for three-phase circuits. For single-phase circuits, the formula is slightly different. The single-phase voltage drop formula is Vd equals 2 times L times R times I divided by 1000, where the variables are the same as in the three-phase formula. The factor of 2 in the single-phase formula accounts for the fact that the current travels through the conductor twice, once in the outgoing leg and once in the return leg. The resistance value used in the voltage drop calculation should be the alternating current resistance, AC resistance, of the conductor. The AC resistance is typically higher than the direct current resistance, DC resistance, due to the skin effect. The skin effect is the tendency of alternating current to flow near the surface of the conductor, which reduces the effective cross-sectional area and increases the resistance. The NEC provides tables of AC resistance values for different conductor sizes and types. These tables should be used to obtain the correct resistance value for the voltage drop calculation. The voltage drop calculation should be performed for each phase of a three-phase circuit. In a balanced three-phase circuit, the voltage drop will be the same in each phase. However, in an unbalanced three-phase circuit, the voltage drop may be different in each phase. In this case, the voltage drop calculation should be performed separately for each phase to ensure that the voltage drop is within acceptable limits. When calculating voltage drop for long cable runs, it may be necessary to consider the effects of inductance and capacitance. Inductance and capacitance can cause the voltage drop to be higher than predicted by the NEC formula. For very long cable runs, it may be necessary to use specialized software to accurately calculate the voltage drop. The NEC provides guidelines for calculating voltage drop in different types of wiring systems, such as conduit, cable tray, and direct burial. The voltage drop calculation should be performed in accordance with the NEC guidelines for the specific wiring system being used. It is crucial to consult the latest edition of the National Electrical Code for the most up-to-date information and requirements regarding voltage drop calculations and conductor sizing. Local amendments to the NEC may also exist, so it's important to check with the local electrical inspector or authority having jurisdiction to ensure compliance with all applicable codes and regulations. The type of conductor material, whether copper or aluminum, also affects the voltage drop. Aluminum conductors have a higher resistance than copper conductors of the same size. Therefore, for the same load and distance, an aluminum conductor will have a higher voltage drop than a copper conductor. The NEC provides resistance values for both copper and aluminum conductors, which should be used in the voltage drop calculation. The ambient temperature also affects the resistance of the conductor. As the temperature increases, the resistance of the conductor increases. Therefore, the voltage drop will be higher at higher temperatures. The NEC provides temperature correction factors that can be used to adjust the resistance value for different ambient temperatures. These correction factors should be applied to the resistance value before calculating the voltage drop. The altitude also affects the ampacity of the conductor. As the altitude increases, the air becomes thinner, which reduces the cooling effect of the air on the conductor. Therefore, the ampacity of the conductor is reduced at higher altitudes. The NEC provides altitude correction factors that can be used to adjust the ampacity of the conductor for different altitudes. These correction factors should be applied to the ampacity of the conductor before selecting the conductor size. In summary, calculating voltage drop is essential for ensuring the safe and efficient operation of electrical systems. By following the NEC guidelines and considering all relevant factors, such as conductor size, material, temperature, and altitude, engineers and electricians can select conductor sizes that will minimize voltage drop and ensure that electrical equipment operates properly.